All right, hi everyone. My name is Phúc, and my team and I today are going to talk about MSTD sets in finite non-abelian groups. So before we start, let's go through some of the definitions. A finite subset S of a group G, where we write the operation of the group additively, we define the subset to be the sum of all of the two elements S1 and S2 taken out from S. And the difference set is defined similarly. So a finite set S is called MSTD, which stands for more sum than difference if the cardinality of the subset is greater than that of the difference set, and MDTS if the opposite holds, and balanced if the difference and subset have the same cardinality. First, we take a look at a couple of results in the integers. So a theorem by Martin-O'Brien states that let P be the sets of all integers from 0 to n. Then for n greater than or equal to 14, there is a positive proportion of the subsets of P that are MSTD and DTS and balanced respectively. And Zhao proved an improved version of this theorem, which is that the proportion of MSTD and DTS and balanced subsets all converges to their respective positive limits as n goes to infinity. So Zhao proved that the proportion of MSTD subsets is greater than 4.28 times 10 to the minus 4. And the Monte Carlo experiment suggested that this limit is approximately 4.5 times 10 to the minus 4. So we differentiate between MSTD subsets in integers and finite groups. So in looking at subsets of the integer, we usually look at fringes, which consist of the left and right fringes, which we denoted as blue in the figure, and red, as we denoted, and the middle elements, which we denoted as red here. So the more in the middle the elements are, the higher probability it can be in the subset of a randomly chosen subset of the integers from 0 to n. The reason is that, for example, if we take, say, n, then n can be written as the sum of elements from 0 to n in roughly n over 2 ways. But for number 1, for example, it can only be written in one way as the sum of the elements in 0 to n, namely the sum of 0 and 1. So 1 has a lower probability of being in a randomly chosen subset than n. However, we do not have that kind of fringe structure in finite group because unlike in Z, you do not have this kind of ordering that respects addition. So for example, if we take a look at Z mod NZ, we see that everything wraps around in a circle, and so we cannot have this kind of fringe structure because each element has the same probability of being in a randomly chosen subset. That's why we take a different approach when we look at subsets of finite groups instead of the integers. So a theorem by Zhao states that the number of MSTD subsets of NZ mod NZ is approximately 3 to the n over 2 for odd n, and n times phi to the n over 2 for even n, where phi is the golden ratio. Also, the number of MSTD subsets of Z mod NZ times Z mod 2Z is approximately 3 to the n plus 1 for odd n and 3 to the n for even n. So in general, when we take a look at finite groups which are not necessarily abelian, interesting thing happens. So a theorem proven by Miller and Visuet states that if Gn is a family of finite group such that their size tends to infinity, and Sn is a uniformly randomly chosen subset of Gn, then the probability that the subset and the different sets of Sn both equals to the whole group tends to 1 as n goes to infinity. And we sketch an outline of the proof. So first, we fix an element G in the group G, and then we form a partition of the group Gn into chains. And in each chain X, it satisfies the following equation. And then we show that the probability that G does not belong to the sum set or the difference set are each the expression on the left-hand side, where L denotes the Luca number. And then we take the product over all of the partition. And then we bound the Luca number from above by 1.8 to the size of X. And then note that since X is the partition of G, when we sum all the size of X, we get exactly Gn. And so it is bounded above by 0.9 to the Gn, which tends to 0 as n goes to infinity, because the size of Gn goes to infinity.
Okay, I'm John Haviland. I'll be talking about the dihedral group. So the dihedral group is an example of a finite non-abelian group where we can study the sum sets and difference sets because there's a lot of structure that we can exploit. So we're doing this following Miller and Visuit, who examined this in addition to the general results they had in their 2014 paper. So they also looked at the dihedral group. They started off with some probabilistic results in Z mod NZ because Z mod NZ and the dihedral group are very closely related. So specifically, they looked at the probabilities that elements would not be in a sum set or a difference set. So when taking a sum set of a set with itself, they found asymptotic results like this. And when adding two different sets or subtracting two different sets, they found precise results here. So these are the probabilities we have in Z mod NZ, but how to apply this in the dihedral group. So what we do is we decompose a subset S of the dihedral group into R and F, where R is the rotation elements and F are the reflection elements. So when we do this, we can try to figure out, well, what are the rotations in the sum set and what are the reflections in the sum set? And the same thing for the difference set. So when we look at this, we see that there's actually some sets that are shared between S plus S and S minus S. So the unique contributions are that S plus S has contributions from R plus R and negative R plus F, whereas S minus S has contributions from R minus R. So we can see here that S plus S gets unique contributions from two different sets, whereas S minus S gets unique contributions only from one set. This leads to the conjecture that there are more MSTD than MDTS sets, subsets of D2N, because there's more contribution to the sum sets than to the different sets. So to try to prove this, we're going to examine the expected sizes, the expected contributions of R plus R, negative R plus F, and R minus R. So to do this, we're going to start off by improving one of Miller and Visuit's asymptotic results to an exact result. So what we're doing here is just computing the constant for the probability that an element is not in the sum set of a set with itself. So we knew before that it was asymptotically 3/4 to the n over 2, but now we know exactly how the growth is related to that. We have this constant here. So the way we prove this is just by finding exact probabilities when we know the parity of k and n. This is done with Miller and Visuit's methods. And then we can take an average over the different parities. And through this averaging process, we get this nice constant out at the end. So now using these exact results that we have, we can find the expected size of R plus R and negative R plus F. And the way we do this is just, for both of these, we find the probability that an element is in these sets by subtracting the probability that it's not from 1. So, so these two probabilities here are the probabilities that an element is in R plus R, given that it's possible. And then we multiply that by n, which is the number of possible elements of R plus R. So for R plus R, all of the possible elements are rotations, and there are n rotations. So this is how we find the expected size for R plus R, and the same process goes for negative R plus F, where we already had the exact probability. So now we can easily compute the expected size of both sets, which is the expected contribution of both sets. So we can figure out exactly what this will be on average. So now that we know the expected contribution from R plus R and negative R plus F to S plus S, which is the sum set of our original set, we want to figure out what the expected contribution to the difference set is by R minus R. We know that it's at most n because every element of R minus R is a rotation element. And there are only n rotation elements in all of D2n. This means overall that the expected size of r minus r is certainly at most n, because r minus r is always at most n. So if we want to now compare this to, we want to compare r minus r to r plus r and negative r plus f. To do this, we can just compare the expected sizes, which we've just computed. So on the previous slide, we found this formula for the expected size of r plus r and negative r plus f. And we know that if it's greater than or equal to n, then it's certainly greater than or equal to the expected size of r minus r. So these two things are equivalent. And in fact, this does hold whenever n is greater than 3. So we can see that as long as n is greater than 3, the expected contribution from r plus r and negative r plus f is greater than the expected contribution from r minus r. So this is just kind of formalizing our idea that the sum set gets more contribution than the difference set gets. So taking this back to the original proposition that we want to show, we need to figure out how this contributes to showing that there are more MSTD sets than MDTS. So what's important here is that just because the contribution for the sum set, which is this r plus r and negative r plus f, just because that's greater than r minus r, that does not at all mean that s plus s is greater, has more elements than s minus s. So for example, if s is greater than n, if the size of s is greater than n, then both the sum set and the difference set are all of D2n, but this above result will still hold. In particular, we could have, so in particular in this case, usually what happens is that r plus r and negative r plus, and r minus r are both all of the rotation elements. They both contain all the rotation elements. So those two sets are equal. So just the fact that we have any reflection elements from negative r plus f, that will mean that the left-hand side of this equation is bigger, but the sum set and the difference set overall still have the same size. So we need to consider this overlap with f plus f and r plus f, which contribute to both the sum set and the difference set to figure out the actual expected size of s plus s minus s minus s, and taking the sizes there. So in order to do this, there's a more nuanced analysis that we need to be able to do. And that's what we'll be working towards in the future.
Hello, my name is John Lentfer, and next I'll be talking about some research we did using Cayley tables for the dihedral group. So let's just remind ourselves what a Cayley table is. It's a table that describes the structure of a finite group by showing all combinations of two elements with the group operation. So here we can see we've also divided our Cayley table into 4 quadrants based on whether there are 2 rotation elements, 1 rotation and a reflection element, or 2 reflection elements. Additionally, the elements in orange are elements that are asymmetric across the main diagonal, and these asymmetric elements are important and come into play because when you have a pair of asymmetric elements, that contributes to more elements being in the sum or difference set than if you were to have just symmetric elements. Okay, and the next thing is what we've been calling an inverse column Cayley table. This is basically the same as the Cayley table, except it uses the inverse of the group operation instead of the group operation. And we've been calling it inverse column because you first start with the element that labels the row, and then you apply the inverse of the group operation to the label on the column. And so this, again, you can see we've labeled the quadrants and asymmetric elements are orange. And you might notice that this table has less asymmetric elements than in the previous table. Okay, so we use these Cayley tables and inverse column Cayley tables, which we call for short just the plus and minus tables, to find formulas for the number of asymmetric elements. And when we were drawing tables just in general for arbitrary n, we noticed that there are some small differences when n is odd or even. And in the end, we found for the plus table, the number of asymmetric elements is the following expression. Likewise, for the minus table, we get the subsequent expression. And then these two have the floor function, and there's an expression over 2 just to account for the differences between odd and even. And then From this point, just by a simple algebra argument, you can show that there are in fact more asymmetric elements in the plus table than in the minus table for the dihedral group for n greater than or equal to 3. So now, again, we ask how can we use that result to help us show that the probability of a subset being MSTD would be greater than being MDTS. So we're going to begin by conditioning on the size of the subset A. So first notice that if the size of the subset A is 1, then the sum set is also going to be 1 element, and the difference set is going to be 1 element as well. So in this case, every subset of the dihedral group of size 1 is going to be balanced. And then also, if the size of A is greater than n, so that means it has more than half of the elements in the group, then both the sum set and the difference set are going to be the entire dihedral group and then thus be balanced. So we need to look at when the size of A is between 2 and n. So when the size of A is 2, there are 3 possibilities for the distribution of the size of R and size of F. And just a reminder, R is the rotation elements and F is the reflection elements. So you could have 2 and 0, 1 and 1, or 1 and 2. And by conditioning on these 3 different possibilities, using the law of total probability, we get the following expression. And just expanding it out. So this was the probability of it being MSTD, and then we do a similar thing to get the probability of it being MDTS, just expanding it out using the law of total probability again. And we get an expression that is a function in terms of m for the probability of it being MSTD given that the size of A is 2, and we get the probability of it being MDTS given that the size of A is 2 to be 0. So since one is positive and the other is 0, we get this lemma that the first expression is greater than the latter. So now we need to look at sets of sizes between 3 and n. Another result that we have is for odd n, the probability of a set being MDTS is given that the size of A is n is 0. And so, in other words, there are no MDTS subsets of size n of D2n for odd n. Okay, the next thing that we looked at is what we've been calling an injective mappings method. So now that we know that for when the size of A is 2, there are strictly more MSTD sets than MDTS sets, one possible proof method to continue with is to show that for each other value of the size of A, so that would be from 3 up to n, there are just at least as many MSTD sets as MDTS sets. So this is an improvement because we no longer have to show that it is strictly greater, it would just have to be at least as many. And now this isn't the only way to approach filling in the gap between 3 and n, but it's definitely one method. And then so one way to show that last statement would be to construct an injection from all MDTS sets to MSTD sets given a certain size A. And then this, if we were able to find such an injection, this would complete the proof of the main conjecture. Okay, next is the conclusion. And so for our future work, we are very close, but we have not quite finished, proving that there are more MSTD than MDTS sets in the dihedral group. We have several different methods that we're using to attack this. The first is exploring interactions between R plus R, R minus R, and F plus F in subsets of the dihedral group. The second is extending the Cayley tables approach for the size of A ranging from 3 to n. And the final method is finding an injective mapping from MDTS sets to MSTD sets. Here are references. Thank you for your attention, and we'd be happy to answer any questions over email.